Hello everybody. In this section we study polynomial functions of any degree. So before we work with polynomial functions, we shall define the polynomial functions. So what are polynomial functions? I have already defined this in my earlier videos, but there are certain terms like what are the constant term, what is the coefficient, and etc., leading coefficient and leading term. So to define all that, I will redefine the polynomial functions. A polynomial function, I will abbreviate polynomial functions as PF. That is my abbreviation. Polynomial function of degree n. Degree n is a function of the form, so which is denoted by P of x is equal to a n x power n plus a n minus 1 x power n minus 1 plus and so on. It will go on up to a1 x plus a naught. So where n is a non-negative integer. So n is a non-negative integer in the sense it can be 0 or it can be greater than 0, and an is not equal to 0. So the degree of the polynomial function is said to be n. So these coefficients, that is an minus 1 and so on, a1 and a0, are all called coefficients of the polynomial. And you have a constant, that is a naught. So a naught is the constant coefficient or the constant term, constant coefficient. How is it the coefficient? As I told you earlier, it is the coefficient of x to the power of 0, which is nothing but 1. So it is the constant coefficient or constant term of the polynomial. And you have an to be the coefficient of this is the coefficient of highest power of x, right? Highest power of x. So this is called as leading coefficient, leading coefficient, as well as it can also, and the term together is called as an x power n is this one term. This is called as leading term. Okay, so for example, if I consider 3x power 5 plus 6x power 4 plus minus 2x cube plus x square plus 7x minus 6. So here this negative 6 is nothing but the constant term or the constant coefficient, and the leading coefficient is 3. This is leading coefficient, okay, and the leading term is 3x to the power of 5. This is the leading, okay. So I have the leading term above. Okay, I'll just point it to that. Okay, this is the leading term. Fine, and the degree of this polynomial is x power 5. Sorry, degree is 5, just 5. So what are all the coefficients? The coefficients are 3, 6, negative 2, 1, 7 and negative 6. These are all the coefficients of the above polynomial. So there are some famous graphs that I will be talking about. So that is graphic basic polynomial functions. So the simplest polynomial functions are monomials of the form p of x is equal to x to the power of n, whose graph is like this. It looks like okay, so yeah, I will be needing many coordinate planes. Okay, so this is x, y, x-axis, y-axis, x-axis, y-axis. Okay, so this is nothing but the straight line. This straight line is nothing but y is equal to x. And if you have a parabola, so this is 0 and its width will be between. So if you have a parabola like this, I'm sorry, my curve looks like a bent rod. Okay, so this is nothing but y is equal to x square. So then you have y is equal to x cube, which looks like okay, which looks like this. So this is y is equal to x cube. So the same thing will continue with y is equal to x to the power of 4. It will be very similar to this graph, but the thing is it will be little wider than this graph. Okay, so it looks little wider as if it is stretched. And even y is equal to x to the power of 5, that is if it is an odd power, it looks the same way, but it looks as if it is stretched in the y-axis. Okay, so these are the basic graphs. So you will have to know like graphs of basic polynomials, which are nothing but monomials. So you'll have to know how these graphs look like immediately as soon as you see the graph, you will be able to find out what exactly is the equation of the graph. Okay, so moving further, graphs of polynomial functions and their end behavior. So graphs of PFs and their end behavior. Okay, so the graphs of polynomials of degree 0 and or 1 are lines. So we have discussed that already, and degree 2 are parabolas. So as the degree becomes higher and higher of the polynomial, the graph will become complicated. But the graph of a polynomial functions is always continuous. That means there are no breaks and there are no holes. So once you see the graph, if there are breaks and holes, you can identify that this is not a graph of a polynomial function. And more than that, the graph will have a smooth curve. Okay, you cannot have cusps or corners. So if you see cusps or corners, that means that like pointed edges or pointed edges, both are one kind of pointed edges. I will draw the graph for you to get a better idea. So even then the particular graph will not be of a polynomial function. So for example, so if I have a graph like this, so hole is nothing but a hollow circle. That there is an hollow circle. This is a hole and this is a break. There is a break, correct? There is a break in this region. So break and hole. So therefore this particular graph, okay, if the color is confusing you, all right. Okay, so now the red color part of the graph, that is lines are represent the graph. So you can see that there is a break of the graph as well as there is a hole in the graph. So this is not a graph of a polynomial function. Okay, the same thing applies to what I said with the corners and cusps. So what is a cusp and how does a corner look? So let me draw a corner. So this is a corner and this is a cusp. Okay, so this is a corner and this is a cusp. So because these two things will tell that the graph is not smooth, therefore this is also not a graph of a polynomial function. So if there are no such things, like if there is no break, no hole, no corner, no cusps, they are all polynomial functions. Like you will see that they are very smooth. Okay, something like this. Fine. So I'm sorry. Yeah. Okay. So the red line represents the graph of the polynomial function. So this is definitely a polynomial function because there are no breaks, there are no holes, there are no corners, or there are no cusps. So this is how you identify this is a graph of a polynomial function. So the domain of a polynomial function is set of all real numbers. So we can sketch only a small portion of the graph. That is, we cannot include the negative infinity to positive infinity, but you can sketch only a small portion of this graph. But the values for x outside the portion of the graph we have drawn, we can describe the behavior of the graph. That is nothing but the end behavior. So the end behavior of a polynomial is a description of what happens as x becomes large in the positive and negative direction. In the positive and negative direction. So to describe the end behavior, we will use the following notations, so which are called as arrow notations. So the notations are, if x tends to infinity, that is, it is increasing on the positive side, this means that x increases without bound. And if you have x tends to negative infinity, that is x goes to negative infinity, that is x decreases without bound. Okay, so for example, if you consider y is equal to x square, so y is equal to x square in the sense, you take input values to be negative or positive. If you square them, you are definite that you will get the output always to be positive, right? So therefore that means y tends to infinity as x will tend to infinity, and y again tends to infinity as x will tend to negative infinity. Even if x is taking negative values, y is tending to infinity with both the cases. But that is not the same if you consider y is equal to x cube. So y is equal to x cube has y tending to infinity only if x tends to positive infinity, and y tending to negative infinity if x tends to negative infinity. So this is how you judge the end behavior. The end behavior is determined by the term that contains the highest power of x. So in a polynomial function, an x power n is nothing but the highest term of x. So based on that term, we will judge the end behavior. Okay, so the highest power will always be the highest power term is nothing but a term of the form of a basic polynomial. Either it has to be in this form or it has to be in this form. So that is judging the highest power term. So we can judge the end behavior of the polynomials. So to sum up whatever I said now, so if then the end behavior of the polynomial p of x, which is equal to an x power n plus an minus 1 x power n minus 1 plus and so on plus ax plus a naught, is determined by degree n, is determined by degree n, and the sign of the leading coefficient and the sign of the leading coefficient an, as indicated in the graph. So the graphs that I will be drawing is okay. This graph is something like this. Okay, so here you see that the leading coefficient is positive. So here in this region, that is, I will highlight the region in green. So in this region, y will tend to infinity as x tends to infinity, correct? And here in the bottom region, so y is tending towards negative infinity as x tends to negative infinity. So if you have the opposite of this, that is, if you have a graph something like this, okay, so the green part tells you that y is tending to positive infinity as x tends to negative infinity, because it is in the second quadrant, and the blue part will imply that y tends to negative infinity as x tends to positive infinity. Okay, because the graph is in the third quadrant. Okay, so in this case, in the first case, you have the leading coefficient positive. In the first case, leading coefficient is positive, and in this case, leading coefficient is negative. Okay, so there is other possibility also. So let me draw two more graphs for you. So if the graph looks like this, okay, so you can see that the end functions, the end points are it will extend up to infinity, but they are in the first and second quadrant. So the green part, this part, the one in the first quadrant, tells you that y tends to infinity as x tends to infinity, and the blue part, this one, another end point or another end part of the function, so that tells you that y tends to positive infinity again, even if x is tending to negative infinity. So even in this case, we say that the leading coefficient is positive. Okay, and the second case here, if you have the graph like this, that is the reverse of the other graph. So here you can see both the end parts of the functions are in third and fourth quadrant, and that implies that as x tends to positive infinity, y is negative, and as x tends to negative infinity, y is positive. Y is negative again. Okay, so this will be an example for leading coefficient being negative. Okay, so that is how you judge the end behavior of a polynomial. Given a polynomial, you can determine it by judging the leading coefficient. So let us do an exercise problem. Say I will consider problem number 12. So this is nothing but a polynomial function is given. Describe the end behavior of the polynomial function. Match the polynomial function with one of the graphs. That is 1, 2. Okay, you have graphs below. So you can match it after you plot it or judge the end behavior. S of x is said to be half x to the power of 6 minus 2x to the power of 4. So which is the leading coefficient here? 1 over 2 is the leading coefficient and 1 over 2 is positive. Okay, when 1 over 2 is positive, what do we have? We have that y will tend to negative, that is s of x is y here. S of x will tend to infinity when x tends to infinity as well as x tends to negative infinity, correct? Okay, so let us check the graph by plotting it. So the graph is y is equal to 1 divided by 2 x power 6 x power x power 6 minus 2 x to the power of 4. So you can see that what I said, like even if the x takes negative value, the y values are on the positive side. That is, the y values are the graph, the end points of the graphs are in first and second quadrant. Therefore, the end behavior matches with what I said, and the graph matches with number 2. So 12 matches with the number 2, that you can refer to the textbook. There is a picture. So 12, graph of 12 is equal to Roman numeral 2. So this is how you judge the end behavior of a polynomial, analyzing the leading coefficient of a polynomial. Okay, I'll end this video here. In the next video, we will learn about using zeros to graph polynomials. Zeros are nothing but roots. So that is, if you substitute that particular number, a number a is said to be a 0. If you substitute a into the polynomial, you get back the polynomial to be equal to 0 upon simplification. So see you soon. Thank you for listening.